Hello there guys, welcome back to another epic inexorable maths video. In this video we want to find the Laplace transform of the derivative of f of t. So we've already looked at how you find the derivative of polynomials and things like x to the power of a half, sine, cosine, exponential functions. What about the derivative of a function? Why would we do that? Let's talk about that for a second. First of all, one of the primary purposes of a Laplace transform is to solve differential equations. And the way that we do that, we haven't done it yet, but if you're familiar, and if you're not, it's okay, the way that we solve differential equations with a Laplace transform is by taking the Laplace transform of every single term, which means we need to take the Laplace transform of the derivatives as well. So it's really important to know what the derivative of the, what the Laplace transform of the derivative is. So let's just dive straight in and do it. It's really not too bad. So, from the definition of the Laplace transform, this is the integral from 0 to infinity of the derivative of f of t times e to the negative st dt, just like that. That's the definition of what it is. Lovely, lovely. Okay, now we could potentially try and work out what this is. Maybe we could use integration by parts, right? Because it's a product. So let's do integration by parts. We need to have a u and we need to have a dv dt. Okay, well, just bearing in mind here that one of the functions is a derivative, which means we kind of know what it integrates to, or at least we know what it integrates to in terms of f of t. It's just going to become f of t when it integrates, which is very nice. So why don't we let that be what's going to get integrated? So in other words, let's let it be dv dt. So the derivative of that, because we want to integrate it. And then that means that u will be e to the negative st, like that. Okay. That also means, just doing these, that du dt would be minus se to the minus st. And it means that v would just be f of t if we integrate that one. Okay. Plugging it all back in then, you've got u times v. So f of t times e to the negative st. And that's from 0 to infinity, minus, and then we want the integral from 0 to infinity of the other two. So this is going to be f of t times minus se to the minus st. So the minus s, I'm going to bring out the front and make that a plus s there. And then I've just got f of t times e to the minus st dt, just like that. But hold on a second, look at this. This right here is literally the Laplace transform of the original function, isn't it? You see that there, that integral, it's actually the exact same integral, which means this is just f of s, or fancy L of f of t. But I'm going to call this f of s. So we'll do that in just a moment. Okay. So again, you really should, if you're doing this formally, you should put in a limit here and say, as you know, the limit, make up some variable, maybe something like y, as y goes to infinity of f of y e to the minus sy, because you can't really just substitute it in, but we're going to kind of do it in an informal way here, and we're just going to say, well, as infinity goes in here, as we take the limit, this is going to become 0. So 0 minus, substituting 0 in, actually substituting 0 in, you get f of 0 times e to the minus s times 0. So that's just e to the 0, which is 1. So it's just this. So one thing to mention, though, by the way, is that this first value here, so like f of t e to the minus st, as t goes to infinity, the only time where this will actually go to 0, there's a couple of situations we need to just make a note of. First of all, s needs to be greater than 0, because if it wasn't greater than 0, if it was negative, negative s would be positive, and at e to the positive infinity is not going to go to 0. So s needs to be positive so that minus s can be negative, and so we can actually say that that's 0. Equally, f of t needs to be of exponential order or below. which basically means it can't be a function that will go to infinity faster than this one decays. So for example, if f of t was something like e to the power of t squared, then this would not be 0. We can clearly see, because that would grow much faster than that one. And that's actually why that for example, e to the power of t squared doesn't have a Laplace transform, because this doesn't work. So just take that in mind. F of t here cannot be something that's of exponential order, or sorry, above exponential order. So it can't be things that go to infinity faster than e to the minus st decays to 0, if that makes sense. Okay, that's just a quick note. And again, s needs to be greater than 0, but it's all just formalities, guys. Anyways, so we've got an s there, and then this here, this is the Laplace transform of the original function, which I call f of s, right? It's f of s. It's curly L of f of t, but if you want to make it a bit more concise, it's a function of s. It's the integrated function of s. So it's capital F of s there. That's a lowercase, that's an uppercase f. Okay, lovely. And then we're basically done, because we can just swap the order of the terms around. You end up with s times capital F of s minus f of 0. And that's a lowercase. So what we've got here is that the Laplace transform of the derivative of the function of t is just s times the Laplace transform of the original function of t minus the original function evaluated at 0, if that makes sense. So that is everything, guys. That is how you take the Laplace transform of the derivative of f of t. Thank you guys so much for watching. Highly appreciate it. And I'll see you in the next video.